Okay, for these, we're taking notes on notebook paper. All right, make sure they are thorough, meaning you're getting all the information that you need. Okay, and then you're going to scan these guys and submit to Blackboard. Section 2.4, chemical reactions. Okay, so what is a chemical reaction? Chemical reactions are how substances change into different substances by the breaking and forming of chemical bonds. Now, these can be both covalent bonds or ionic bonds, either one. Okay, so covalent or ionic. Okay, or every living thing is going to build up and break down molecules to help them carrying out their cellular process. This could be digestion, cellular respiration, photosynthesis, growth, repair. All these things that an organism is going to have to do to survive is going to take place by chemical reactions, or the making, building up, or breaking down of molecules. Okay, in all chemical reactions, there are two things. There's a reactant, so we need to know what is a reactant, and there's a product. And the reactants are the things or the substances that are being changed during a chemical reaction. Okay, the products are the substances that are made or produced by a chemical reaction. So in this example here, this is methane, a gas, being oxidized by oxygen gas. This is combusting it to form CO2 and water. This is the same reaction that takes place when you turn on the stove in your house. Methane gas combines with the oxygen and it burns to produce CO2, carbon dioxide, and water. This side of it, these guys over here, would be the reactants. Okay, reactants, because they are at the end of the arrow that doesn't have the point. Arrow's going that way, right? These things over here are the products, because these are what are produced or formed through this combustion of oxygen. We have carbon dioxide and water. The things that are shown by a chemical equation are what substances are changed and what substances are formed. And that's also going to tell the amount, relative amounts of what's being changed and what's being formed. So in this case, this two hydrogen gas molecules, H2 is hydrogen gas, and one molecule of oxygen gas are being combined. So these are the reactants. They're combined because they're producing water on this side. So again, reactants over here. This is the direction of the reaction, and over here this is the product. Okay, so the coefficient in front tells you the number of molecules. This is a molecule of hydrogen gas. Okay, this is 1 because there's no coefficient. Molecule of oxygen produces 2 coefficient molecules of water. Okay, so the substances are changed are hydrogen gas and oxygen gas to produce water. Okay, what is bond energy, and do all atoms have the same bond energy? The bond energy is the amount of energy holding the atoms together. When bonds form, the electrons in the energy levels are being transferred or shared, so that's where this energy is coming from. Different atoms are going to require different amounts of bond energy. Different amounts of bond energy because they're going to either be sharing so many electrons or transferring so many electrons, and the amount of electrons are changing and will contribute to the bond energy. Okay, so bond energy is required to both make the bonds and break the bonds. So how does the amount of energy that is released compare to the amount of energy that breaks the same bond? The amount of energy that makes and breaks bonds, the same bond, is the same. When water is formed, it takes the same amount of bond energy as when the water is broken apart. So in this example here, this is hydrogen gas, oxygen gas being combined to form water, right? Hydrogen gas, oxygen gas, combined to form water. If this reaction were reversed, where we're breaking the water, the energy required to break these bonds between the oxygens and hydrogens of water would be the same as it took to form the water from hydrogens and oxygens in the first place. So what do arrows pointing in opposite directions indicate, and what happens when chemical equilibrium has been reached? Okay, a lot of reactions are reversible, okay, meaning the reactants will form to make this product, and that product can be broken down into the same reactants from which it was formed from in the first place. So the reactions can move in both directions at the same time, which means the arrows will be shown in opposite directions at the same time. When reactions take place at the same rate in both directions, the reactant and product concentrations remain the same. So if they're the same, what it means is there is a state of equilibrium for this reaction. And the reactants and the products are being made at the same rate. The reactants will form the products, and the products will get broken down into the reactants at about the same rate. And this happens often. Okay, so what things do all chemical reactions involve? Okay, all chemical reactions involve a change in energy. And remember, bonds are being formed by either sharing electrons or transferring of electrons. And so these electrons that are in these energy levels of the atoms involved are going to change energy. Okay, energy that is added can break bonds, and new bonds form, and energy is released. Okay, it means that energy is both absorbed and released in every reaction. Some reactions are going to release more energy than they absorb, and some reactions are going to absorb more than they release. Okay, so think of it this way. If they're releasing more than they absorb, that would mean that the reactants have more energy than the products, and during the formation of those products, energy will be released as heat or light. Some reactions are going to absorb more than they release, meaning the reactants would have less energy than the product, and energy will be going into those products. Okay, so what is activation energy? Activation energy is the energy needed to make the reaction occur, okay, or the energy needed to start a chemical reaction is the activation energy. Okay, in our little picture here, it shows this guy pushing a rock up the hill. Well, the reaction that we're going to get is we want this rock, this boulder, to roll down the hill. It's not going to roll down the hill until enough energy is applied to get it to go up the hill. So this energy to get this to go up to the top of the hill would be the activation energy. Once it starts rolling, our guy can just let go, because it's gonna go. It'll roll downhill to completion, till it hits flat lines, without any extra help from him. It's not going to start and then stop and then start and then stop. It'll just go to completion. Most chemical reactions, if you can get them to start, they will go to completion. So what is an exothermic reaction? An exothermic reaction is a reaction where it releases more energy than is absorbed, meaning the products, what's produced, has less bond energy than the reactants. So where does this excess energy go? It's released as heat or light. Through the little graph, we have the rate of the amount of energy on this axis, and the course of the reaction, or the time of the reaction, on this axis. The reactants are here. To get the reaction to go, it requires a little bit of energy called activation energy, so it's going to go up. The amount of energy goes up this much, and then this thing's going to go to completion. Where the products down here have less energy, right, because they're this high, less energy than the reactants, this side. So where'd that extra energy go? It was given off as heat or light. An example of reaction given off heat, we like those instant heat packs. It's a pack, it's actually a bag within a bag. There's two chemicals in there. When you break the inside bag, the chemicals mix, makes this exothermic reaction, and heat is produced. Okay, another example of this would be like a glow stick. Again, you have a plastic tube with a smaller tube inside of it. You crack it, the chemicals mix, and it starts glowing, or light is given off. Both of these are examples of exothermic reactions. The products have less energy than the reactants, and so this excess heat, or excess energy, is given off as heat or light. So an endothermic reaction would be the opposite of an exothermic, where the reactants are absorbing more energy. Excuse me, the products are absorbing more energy than the reactants have. Products have a higher bond energy than the reactants. So this energy, this excess energy, is absorbed by the products to make up the difference. Energy has to be accounted for. The reactants are down here. Okay, less energy than the products, which are up here. Remember, this is the amount of energy. The higher up, the more energy. So obviously the reactants, being down, have less energy than products. Activation energy is put in to get this reaction to go. It starts going and it forms our products. Okay, so heat energy is put into our products, and as a result, it cools off. It's going to take energy from the outside, from the environment. This would be like an example of like an instant cold pack. You find a first aid kit, instant ice pack. You have this bag that has a couple of chemicals inside of it. Again, I got a bag within a bag. You crack the inside bag, the chemicals mix. This endothermic reaction takes place, and you get this instant cold pack. Okay, because energy is going in, so it cools off. Okay, so in these two examples, we have photosynthesis and we have cellular respiration. So would photosynthesis be an endothermic or an exothermic reaction? And would cellular respiration be an endothermic or an exothermic reaction? So on this, think about this. We have light energy coming in to our reactions, so there's going to be more energy over here on the product side than in the reactants, putting energy in. So this is going to be an endothermic reaction for photosynthesis. For cellular respiration, which is the opposite reaction, notice these are the products of photosynthesis, which become the reactants of cellular respiration. In this case, sugar, glucose, is being broken down in the presence of oxygen, and it's producing carbon dioxide, water, and energy in the form of ATP. So if energy is coming out as a product, energy is being released. So this is an exothermic reaction.